Friends, today we shall be going to a new topic, one of the most interesting topic in hydraulic engineering, that is rapidly varied flow. Well, and under this rapidly varied flow, as I was telling, this is most interesting topic. The hydraulic jump is one phenomenon which we have referred in our earlier classes also several times, that well, we are getting a phenomenon that we call as hydraulic jump. We will be getting a phenomenon, but we couldn't discuss that earlier. Now today we will be discussing under the topic of rapidly varied flow, the hydraulic jump. Well, so before going to hydraulic jump, let us see what we have discussed earlier till now. That is, we started with uniform flow, and there we did discuss about resistance flow formula, and then we did discuss how using that resistance flow formula we can compute the uniform flow depth, that is the normal depth. And then we studied critical flow also, and then critical flow is quite important, or we need to recall the understanding of our critical flow for studying this hydraulic jump phenomenon. Say we did discuss about various conditions that we get at critical flow condition. Critical flow itself is a condition, and that critical flow condition corresponds to some of the very important aspect, that is the specific energy is minimum at critical flow, or you get specific force is minimum at critical flow. Like that we got different conditions. Froude number is 1, Froude number is 1 at critical flow, all those we got. And then based on the concept of critical flow, we classified the flow into two classes. One is called supercritical flow, another is called subcritical flow. Well, the supercritical flow means when the flow depth is less than critical depth, or rather we can say when the flow velocity is greater than critical depth velocity, that is velocity at critical depth. Velocity at critical depth is something, and in supercritical flow velocity will be higher than depth. So that is called supercritical flow, or visually we can say when depth is less than critical depth, then say it is supercritical. When depth is greater than critical, then it is called subcritical. Well, so that way we classified that things. And then of course we have studied gradually varied flow, then how the flow changes gradually over the long reach of channel, long channel reach. So when the flow depth changes, because this rapidly varied flow is also a phenomenon where the flow depth changes, and gradually varied flow is also a phenomenon where the flow depth changes. So in gradually varied flow, the flow depth changes slowly, or rather gradually, within a long reach of the channel. If we recall our last class where we could solve one problem of gradually varied flow using standard step method, there we could see that when the flow depth were raised to 2 meter from a uniform flow depth of 0.335 meter, no, from a uniform flow depth of 1.268 meter or 1.27 meter around, that is from 1.27 to 2 meter when the depth was changed, and of course in a very mild slope. The slope, if I remember correctly, that was 1 into 10 to the power minus 4. So that was the slope, bed slope. So when in that bed slope we change the depth of flow in that small amount, I mean even less than 1 meter change of depth was from 1.27 to it was 2 meters. So it is slightly higher than 0.7 meter when it was raised. Then the gradually varied flow profile that extended up to about 20 kilometer. So now we can have the feel that this flow depth change is so gradual that it is changing in a very long reach of channel. Of course, it is changing very slowly. That means at 20 meter perhaps you will not be able to appreciate the change between the normal depth flow and the changing gradually depth flow, because it is very just a difference of maybe a millimeter, so like that, but it is changing gradually and it is forming ultimately the total change we are having. But in rapidly varied flow, the flow will be changing within a very small reach of the channel. In fact, it changes in such a small reach that frictional effect can be neglected in such a small reach. So, it changes rapidly within a very small reach of channel, and that is why it is called rapidly varied flow. And we did discuss about computation of gradually varied flow earlier, and here we will have to discuss about the computation of gradually varied flow. And while discussing computation of gradually varied flow, while type of gradually varied flow, we could see that sometimes there is something on the upstream which is not gradually varied flow. A gradually varied flow is there. On upstream of that, we can have a hydraulic jam. In the last class also, in the mathematical computation of one of the gradually varied flow, when it was S1 profile, then we could see that there is a hydraulic jump before that. But what is that hydraulic jump and how it happens, and how we will have to introduce that hydraulic jump, where that hydraulic jump will occur, location of that hydraulic jump, all those issues need to be clear. Then only we will be able to draw the complete flow profile. Till now we are drawing flow profile having gradually varied flow. Now when hydraulic jump is also there in between, the total flow profile we will have to draw, knowing the location of hydraulic jump, the change of depth between upstream and downstream of hydraulic jump, and then how it will continue with the gradually varied flow lying at upstream or lying at downstream. So, all those aspects we will be discussing in this particular topic of rapidly varied flow. And of course, we are always talking about hydraulic jump, but what other gradually rapidly varied flow are there? Well, there can be other type of rapidly varied flow also, which is not hydraulic jump. Well, what is hydraulic jump, that I will explain again, but say in a channel transition, when the channel changes from a say bigger dimension to a smaller dimension, then there can be flow variation, or there can be variation of depth rapidly. So, that sort of flow phenomenon are also falling under rapidly varied flow. Then sometimes in a channel, say we are providing a hump. If you refer to the slide, say the flow is like that and it was flowing like this, then we are providing a raised hump in this part, then the flow depth here you will be observing that will be moving like that. This part of flow is also not a gradually varied flow, so it is a rapidly varied flow. Similarly, in channel transition also we can have that, means when the channel is changing from here to here like that, say this is changing like that, these are the side, and if I draw it in this way, then flow is coming like this, and in this portion it may come down in this way. Why I am using the term may? Because whether it will come down or whether it will rise, in this phenomenon also whether it will come down or rise, this will depend on what type of approaching flow is, whether it is subcritical or supercritical. So, that we will be discussing of course later, but what we will be discussing in this class is hydraulic jump. Well, now with this introduction to hydraulic jump, let us try to define hydraulic jump. Let us try to define hydraulic jump. That is, well, when hydraulic jump will occur, that is the first point. When the flow changes, you can refer to the slide, when the flow changes from supercritical to subcritical condition. This is very, very important point to be noted, that flow must change from supercritical condition to subcritical condition. At supercritical, the flow is coming with a very high energy, and then due to some reason, due to some obstruction at downstream, or maybe due to normal channel slope condition itself, the downstream depth is subcritical, then there is the flow changes from supercritical to subcritical abruptly and with lot of turbulence. So, that phenomenon, so when the flow changes from supercritical to subcritical condition, flow depth increases abruptly with formation of turbulent eddies. So, lot of eddy formation will be there, lot of rolling will be there in the water, and that eddy, first it will be a strong eddy, then these eddies will break down and will form some smaller eddies, and then in between air entrainment will be there. And so that way, when it is forming some turbulent eddies and subsequent breaking up of the eddies downstream, as it is moving downstream, this eddies will break up and it will form some smaller eddies, and leading to air entrainment. Some air will get entered into the flow, bubble will be coming up, and these bubbles are also moving up, and then with this entire the flow phenomenon is associated with a huge energy loss, because these eddies are forming, turbulence is being created, and so all this phenomenon, when it is occurring within the flow, then energy is being consumed in that part. And so in hydraulic jam there will be always loss of energy, and this loss of energy, although we think that it is not good in any, for whatever may be the cause, but for water flow phenomenon, for many a time we need to reduce the energy of flow, and for those purpose we use hydraulic engineering. So we use hydraulic jam, So hydraulic jam is a phenomenon that is used also sometimes. That means we try to produce hydraulic jam so that flow energy get dissipated. Well, so for definition of hydraulic jump is concerned, when the flow changes from supercritical to subcritical, then the flow depth changes abruptly with lot of turbulence, with air entrainment into it, and which is associated with loss of energy, and this flow phenomenon, is known as hydraulic jump. And of course, first investigation of this particular phenomenon was carried out by Beaton, and it was in 1818, long back. This phenomenon was observed and it was investigated. Well, but still today also, although it was investigated long back, but as on today also, this phenomenon is interesting and people are working on that to know much of this particular phenomenon. Well, and when hydraulic jump occur, then there will be a depth at upstream of the hydraulic jump and downstream of the hydraulic jump, and that two depths are called sequent depths. Now, if I draw the hydraulic jump, then suppose this is supercritical flow, and say on the downstream we are having subcritical flow, it is subcritical flow. Okay. Now, how it is occurring subcritical flow, that aspect I am not considering right now, but somehow the depth is increasing here and somehow depth is decreasing here. Discharge is same, Q discharge is coming. For the same discharge, we are having supercritical flow here, subcritical flow here. Then the flow from here to here, critical depth may be somewhere here. This is say YC, critical depth line. Then from this point to that point, water will be moving, creating lot of turbulence here. Lot of eddy formation will be there at the beginning, and then it will be smaller eddies, and then it will ultimately goes and finally it will meet this depth, and this phenomenon is called hydraulic jump. And the depth at upstream, this one say Y1, and depth at downstream, this is say Y2. Sometimes people write y dash and y double dash also. Anyway, this Y1 and Y2 are called sequent depths of hydraulic jump. Now, this hydraulic jump, before going to the theory of the hydraulic jump, let us see that in hydraulic engineering why it is becoming that much of important, because this hydraulic jump has lot of practical application, and that is why people are discussing and people are trying to understand more about this hydraulic jump. It has lot of practical application. So, what are those practical application? First, let us see. One practical application is that for energy dissipation at downstream of dam, sluice gate, etc. Well, that is one of the application. What that application is, say we have a dam, here, and then of course, let me draw a spillway section, not the actual dam section. Say water is being released like that. This is dam is like that, and we have storage of water here, and then when water exceed the spillway level, it will be moving like this, and it is moving this way, and then it is moving like this. Now, what problem can arise and why hydraulic jump is necessary here? You can see this height may be very high, this height may be very high, because we can have dam height varying up to say 300 meter high dam. So, like that also we can have, and of course, smaller dam we can have like 30 meter, 20 meter, like that also we can have, but we can have very high dam also. Now, depending on the height of dam, this water will be releasing from a very higher depth. So, when it is coming from a higher depth, it is flowing all through, it is gaining lot of energy, and it is moving with a very high energy in this part. And this part of flow, as it is moving with a high speed, depth will be very low, depth here will be very low, and it will possess lot of energy. Now, when the water with high energy is moving on the surface, this is again on the downstream we are having the river bed. So, what will happen? This high speed water can cause erosion of the river bed, rather it will always erode the river bed, and it will cause lot of damage to the downstream. Now, if we do not do anything in the downstream part, this high speed water will be moving for a significantly longer distance, and then will cause damage to the river bed. And suppose if it is eroding all these things, then this eroded material will be carried downstream, and somewhere it will be deposited at the downstream. That will create another problem. Well, so what is expected is that we need to control this particular flow, and we should not allow this water to move much downstream, and if possible we should try to form a hydraulic jump here where its energy will be dissipated. So, in this portion we need to form a hydraulic jump. If we can do so, its energy will be dissipated, and then at downstream whatever water is flowing, this is flowing with less energy without causing any damage to the river bed. Well, so for that many a time some obstruction is constructed, seal, or this is called stealing basin, and this part is made concrete. So, when this part is concrete, so here suppose it is moving with high speed, this will not cause damage, and water level by this sort of obstruction is raised to certain depth, and this of course we need to design properly, but here by some obstruction we raise the depth in this part, and then we raise the depth to such extent that it become subcritical flow here, it becomes subcritical. This is supercritical, this is supercritical. So, ultimately between this portion, and of course some small block and other things are there, sometimes this approach is not that simple. I mean, stealing basin has lot of other things to do, but of course we are not covering that in detail. Lot of buffle wall, that means small walls will be here in this portion itself. Some wall may be soot block may be there, which will shoot the water in the upward direction like that. So, different things can be done here, but main objective is to raise the depth and to form a hydraulic jump, and that way it is suppose shoots up from this part, and then it is going like this, and from here a hydraulic jump is occurring. Well, and once this hydraulic jump occurs, this energy of flow get dissipated at this point, and then downstream portion it will remain free of danger. So, it is one application of hydraulic jump. Well, then similarly, suppose we have a sluice gate, Well, where we can have sluice gate, suppose we have a channel of this sort, a river is flowing there, another river is coming there, and this is suppose going from a paddy field, just it is not a river, say a stream, and this is a river, which is coming from hilly area and a big catchment suppose, and then this river is carrying lot of water, and this is having a small catchment, and this is having a much bigger catchment, suppose like this, and this is having a small catchment. This is just carrying, this river is carrying the water which is falling here or coming from precipitation into the agricultural field. Now, water is flowing here and it is joining this river, main river. Now, what may happen that because of heavy rainfall in this catchment, let me rub that part, okay. Because of heavy rainfall in this catchment, this river may have flood, and when this river is, level of water is rising in this river, then water from this river, because suppose there is not that much rainfall, and even if it is rainfall is there from a small catchment, the water in this river will not be that much. So, otherwise suppose this area, this catchment is not having flood or any problem, but when this river is rising, then water from this river will flow back into this river, and this area may get flooded. So, to prevent this area from flooding, sometimes we can arrange to have a sluice gate in this portion or gate in this portion. Then when water is rising here, we are closing the gate and water cannot come. So, this is one way that we use for closing the gate, and then we try to prevent some area, and we use sluice gate in this part. And similarly, there may be lot of other application where we are using sluice gate. Say we want to store water, but not a dam, but we want to store water. Say normally water is flowing at this depth, but we want to have a higher depth, then we can use a gate, and then this is a small gate, and then water is kept up to this much. But suppose we want to maintain the water at this much level, so some amount of water we need to release downstream. But say normally in this slope water is moving at a normal depth, but here when we are releasing it from a smaller depth, it will be moving with a high speed, and that may move as a supercritical flow. Okay. And that supercritical flow may cause damage in this part, and as such we can put some barrier and we can do some other activity here, or sometimes with the depth here we need to increase so that we get a hydraulic jump. Otherwise, this flow will move quite long and it may create or it may cause damage to the downstream side. So, that way for sluice gate, for dam, we need to produce a hydraulic jump for safety of the downstream side. Well, so this is one of the application. Then let us see what is the second application. The second application is that to increase the water depth in irrigation canal to divert the water to side canal or to the field. Well, in a irrigation canal, when a irrigation canal is carrying some water, say it is carrying some water, and say in this side it is field, and there may be some small field channels, then water depth is suppose this much, and with this depth water is flowing here, okay, and then field is here. Well, now suppose so for amount of water required is concerned, we can have only this much of depth, because in this normal slope or in this slope, for the required amount of discharge we are getting this much of slope, but we need to carry the water to this side channel. So, there will be some opening here, and our water level must cross this level. So, what we can do, we can have some barrier here, and then we can rise the water, we can allow, or we can have some device, say we can have some gate which will cause a supercritical flow here, and then hydraulic jump will occur, and then water depth is rising and we can carry the water in the downstream side. Or say we are giving a barrier here, then water is rising here, we are carrying this water to the downstream side, then we need to allow the water to move downstream. Then when water we are allowing, again there may be, it may cause erosion here, then for that purpose also we may have to have say hydraulic jump for energy dissipation. So, for this sort of activity also we need hydraulic jump in irrigation canal. Well, then the third application we can mention that to increase the water depth in apron to counteract the uplift pressure. This is another important application to increase the depth of flow in the apron. Say many a time, as we did explain, so we are storing water by this sort of barriers. Okay. Say some gate are there, we are raising this part to reduce the width of the gate and also to for sediment problem, say gate is not obstructed, that way we are doing it, and then say water depth is this much, and then this part is called apron, because as we know that when we will be releasing water or when water will be moving above this part or we are releasing it, water is coming this way, and then this may be sluice gate like this, and then when we are releasing water it is coming like this, and then it will be moving over this bed. Now, while designing this apron, okay, let me just draw it in this form now. Designing this apron, what is that? This is ground level, this is ground level, and I am not going into detail of this part, but what is that? When water level is here, then water level, we do not have any water on this part, some amount of water is going, and if we do not do anything here, then this water level is going in this level. Okay. Now, what is the difference between hydraulic head? This minus that. So, this is the head difference, and so as this is the head difference, hydraulic slope between this and that we can call as this one. Now, when we talk about this particular part of the water, in this part we do not have much problem due to uplift pressure. Now, when water is there, water is percolating through the ground, and it is moving this way. Okay. Now, as the water is percolating, there will be seepage pressure, and otherwise also when this is not impervious, I mean there is a communication, there will be uplift pressure, because water is a continuous through the soil also. So, water will be having some uplift pressure at this point. That uplift pressure is equal to the depth of water here, and then when it is moving, of course, we use different formula, like say how the energy will lost when the water is moving through the soil. Energy, its existing energy will be lost, and this energy will gradually reduce, of course, but still it will be having substantial amount of energy, and then uplift pressure will depends on that remaining energy. Well, so the uplift pressure here will be more, and then here will be like this, here is suppose less, and then this is the energy loss in between, and then we are getting the uplift pressure like that. For this part, suppose this is the uplift pressure, then from the upward side also same pressure is there. So, for this portion of concrete we do not have any problem, we can provide nominal thickness here, because that is not, I mean nominal thickness means for other consideration we need to give design it, but for uplift pressure is concerned, this is not that significant. But for this part of floor, we can see that uplift pressure from this side is say this much, and from the top we do not have sufficient water, we have only this much of water. So, uplift pressure will be quite significant, and then we need to design this floor so that this floor can resist the uplift pressure. So, the thickness of this floor become quite large like that. As we are going down, uplift pressure is reducing and thickness is also reducing, but it is quite large in this direction. Well, this uplift pressure, if we could counteract by increasing the depth of flow here, then we could reduce our depth of flow here. We could reduce our depth of flow here. So, to achieve that, what we can do, that if we put some buffel, well, if we put some chutes block here, then if we put some, say, if we raise this part like that, then what will happen, that water is coming like this and it is rising up to this point and it may generate a hydraulic jump. It may generate a hydraulic jump. So, this part is supercritical, that is subcritical. When it is rising, hydraulic jump is there. So, the depth of water on the apron is also increasing. So, uplift pressure, it can now counterbalance, and that way the requirement of putting additional thickness to resist uplift is not coming into consideration. Well, so again some other problem are associated with this. If the hydraulic jump from here, then there will be suction in this part. To resist that, we need to do something so that hydraulic jump is formed in a proper location, so that that suction we can avoid. Well, those are finer issues that we need to take up as a different topic is hydraulic structure. Right now we just can see that where application of hydraulic jumps are coming. So, this is one issue where hydraulic jump is applied to counterbalance the uplift pressure in case of hydraulic structure. Well, then another we can very simple use is for mixing chemicals. Well, in many of our water distribution system, for water treatment we need to mix chemical. Of course, we can have some stir up the device, and with that we can make stir up and then we can put the mixer there. But one way, suppose in a simple system, suppose it is a irrigation canal and we need to mix fertilizer into water. Now, if we mix the fertilizer into the water in the canal, then it may not get mixed up properly if turbulence is not there. But if we can have some portion where we have turbulence, and if we put the chemical fertilizer or whatever fertilizer it may be, if we put the fertilizer in that point, then the mixing up will be proper. So, that way for mixing up of suppose fertilizer or any chemical in any water distribution system, if we can have a hydraulic jump, there we will be having the turbulence, and at that portion we can mix the chemical. Okay. So, say in an irrigation canal or in any canal, if we have a system of forming hydraulic jump, so normally the flow is moving in this level and it is moving as a very simple flow, and if we mix chemical here, chemical or any admixture other, if we mix here it may be fertilizer or whatever it is, then it will just meet here and it will be it will take time for diffusion and then it may not get mixed up properly. But if we put a gate here, there may be other devices also, then if we allow the flow to move as a supercritical here, suppose normally it is subcritical flow, if we allow the water to move subcritical flow, and then of course this may keep on moving, but we will have to provide some barrier here so that it rises little bit, and then we are having a hydraulic jump and then it is moving and finally it is again coming like this. So, the objective of putting such barrier is to just fix the location of hydraulic jump. Otherwise, hydraulic jump can keep on moving, that we will be coming later. We will be discussing how it can keep on moving. But anyway, if we can form such hydraulic jump and then if we can mix the chemical here, if it is mixed here, the mixing will be proper, because here we have lot of turbulence and that mixer will be perfect, and then it is moving in the downstream direction. So, in this process, this is one application of a hydraulic jump where it can be used for mixing chemical. Again, another application is that sometimes in our say water supply system, the water may be having less amount of oxygen or air entrainment may be required at that point. Generally aeration tank is always there, aeration system is there where we allow the water to move some turbulence. Now, of course, different devices are there. Say if we have somewhere a tank here, say water distribution, water supply system, in any water supply system, say water in water treatment plant rather, from here we allow the water to come this way, and then it is going like this, water is moving, and then say we can have some plate from here, and then this water may be allowed to just move as a jet, and then it is coming like this, and then we can make some step here, so that water is moving over the step and lot of turbulence are getting created, and then from here, this is a tank, suppose from here this water is carried to the next section. This is for aeration we are using. Now similarly, this aeration can also be achieved by forming hydraulic jam. So where these sort of devices are costly, and in a system we need aeration for different purpose, maybe for say biota, like maybe for fish growth or whatever may be the reason. Suppose we need that, we can form some hydraulic jam where it will be taking some air into it, and air entrainment occur, and this become helpful for many activities or many purposes. So that way, that is another use of hydraulic jam. Well, so that way we have seen that hydraulic jam can be used for various purpose. Hydraulic jam can be used for various purposes, and I have just mentioned few of them, and there can be few more uses of hydraulic jam. Well, but these are some of the prime use of hydraulic jam which are commonly adopted. Well, then we can now see with this knowing that its practical importance in our engineering activity. Now we can see that how we know the phenomenon and how we can express the relationship of different parameters involved in the phenomenon into mathematical form, and using the theory of hydraulic jam, how we can now we are telling that okay, we need to control that hydraulic jam should occur here, and then what should be the depth at the downstream point. All those things we need to know. So for that we need to know the very basics of those theory, and let us just go into the equation of hydraulic jam. It is basically coming from momentum equation. In our earlier class also, maybe in our second or third class, we did discuss about the momentum equation, where we did discuss to some extent about this part, and so we will not be going into much detail, but we are starting from, without explaining the very basics, we are going like this. Suppose a flow phenomenon is there, say flow phenomenon is there, there may be hydraulic jam in this part, and then we have that here what are the forces acting on this part, say P1, pressure force P1, pressure force from this side is P2, then frictional resistance we have FF, then suppose air is blowing, then there may be FA, air resistance is also there, and then it is flowing with a velocity V1 and it is flowing out with a velocity V2, the water coming is Q. So these are suppose the system, and then it has a slope theta, it has a slope theta, so weight of the fluid is W, and then component of the weight acting in this direction is say W sin theta, this angle is theta, this is W sin theta. So what we can have using the momentum equation, the force acting in this part is equal to the rate of change of momentum. So rate of change of momentum means momentum per unit time, how it is changing. Well, so that we can write as say force from this direction, we can say P1, then minus P2. Well, that this, and what are the other forces acting in this direction? This is W sin theta, and then opposing force is minus FF, friction force, then minus FA. That way all these opposing forces are there, and that is equal to momentum means say Q is the discharge flowing in unit time, so volume flowing, so mass is equal to rho into Q, and mass into change in velocity is equal to V2 minus V1. Now from this expression we have already discussed this equation, so I am just writing it directly. When theta is small, so when we are discussing about hydraulic jam, then say theta, for small value of theta for small value of theta, what we can do, say sin theta is equal to 0. So or we can say that W sin theta can be neglected. Then as we know that hydraulic jump is occurring in a very small length of the channel. So in that small length also there will be flow is turbulent. So because of that, the small length we can consider that friction is not that much significant. If it is a long channel, friction has something to do, but if it is a very short portion, in that short portion the effect of friction can be neglected. So that way for short length of the channel, what we can say that Ff, that is the friction, and Fa all can be considered equal to 0. So what we are getting, that P1 minus P2 is equal to rho q into V2 minus V1. Okay. Now this expression is basically the relation of momentum equation, and from that we could derive the specific force expression also. And of course, let us see for rectangular channel, if it is a prismatic rectangular channel, how we can have this equation. Suppose it is a prismatic rectangular channel, for that situation how we can how we can just rewrite this equation to have a relationship between the depth at this point, say y1, and depth after the jump y2. How we can have this relation? Let us see. Okay. So starting from this equation, now for a rectangular channel we can have this P1, say P1, pressure is nothing but, so we can have rho g s is the pressure here, here it is 0. So total pressure will be half of base into altitude. This is, well, let me write, we are writing perhaps y, yes, we are writing y. So this is y. So how we can write this? Half of this thing, so half of rho g y square is the pressure force, and it is, we are talking about per unit width. If we talk about a width of b, this will have to be multiplied by b, and this is y1. So P1 minus P2 we can write, say half of rho g y1 square minus half of rho g y2 square, and this b, as it is, suppose here also P2 is also the same, half of rho g y2 square into b. B is same because it is prismatic, so we can write this P1 minus P2 in this form. And then this is equal to q is q here, q is same. So what we can write, mass is equal to rho q and then V2 minus V1. Okay. Now we can try to simplify this expression. Rho and rho will get cancelled. So what we can write, that say rho here, rho is getting cancelled, and as it is a okay, let me write here this part, that half of say g we are bringing common, half of gb, suppose b by 2 into g, then this y1 square minus y2 square, so y1 square minus y2 square, this is equal to this q we can write as v1 y1 into b, that is y1 into b is the area and then velocity into the depth at this point, and then we can write his v2 minus v1. Okay. Now again we can cancel b and b, and then we can write it in this form, that is y1 minus y2 is y1 minus y2 into y1 plus y2. This is equal to, we can write it as 2 will be coming here, twice v1 y1 by g, and then this v2 minus v1 that we have here, we have from continuity equation q, we have v1 y1 equal to v2 y2. So v2 can be written as say v1 y1 by y2. So we can write v2 as v1 y1 by y2 minus v1 Well, now this will lead us to say twice v1 square. We are bringing twice v1 square here and y1 here, and then it is y2 and it is y1 minus y2. So, this y1 minus y2 again, this y1 minus y2 and this y1 minus y2 we can cancel. This will lead to y1 plus y2 is equal to say twice v1 square and y1 by y2. We had one g here, right, g. Well, now this expression we can further simplify. This expression we can further simplify to say h2 by h1 square. If we write here, then it will become h1 plus h2, and this will lead to twice v1 square by g h1. Why we are writing h1 square? Because here earlier we had one h1 sorry y1, here we had y1 okay, we will have to write it as y y2 by y1 square, and this is y1 plus y2 v1 square by g y1. Why we are writing it in this form? That because we are getting here one term v square by v1 square by g. Now, we know one very important term that is called Froude number, and that Froude number is nothing but v square by g y, that is g d we can call, g y call, that is a diff term. So, v square by g y we can have, and that is why we are writing it this expression particularly to have this term. Well, then starting from this expression, what we can have, our basic intention is to have it in this form, that is y2 by y1, y1 y1 I am writing here. Another y1, if I take this inside this bracket, then I will be getting 1 plus y2 by y1. Well, and this is equal to twice f1 square. This is equal to twice f1 square. F is what? The Froude number. F is Froude number at the point 1. F is Froude number at the point 1. So, it is Froude number square. Actually, Froude number is equal to v by root over g y1, v1 by root over g y1. So, we are writing this Froude number square, and this ultimately we can write as say sorry, this is y2 by y1, we can write as y2 by y1 square, this one, plus y2 by y1 minus twice f1 square is equal to 0. Now, this is just becoming a quadratic equation. This is just becoming a quadratic equation, and this quadratic equation can be written to have, suppose it is x square, this part is x square plus x minus a is equal to, suppose that means ax square plus bx plus c is equal to 0. So, we can write say x is equal to, means y2 by y1 is our variable here, y2 by y1 is equal to say minus b plus minus root over a square. So, the popular expression we can write minus b means minus 1 here, b is minus 1, then plus minus root over b square means again 1, b square minus 4ac. So, minus 4 is 4, then a is 1 and c is minus 2. So, it is minus 2. So, into 1, 4 into 1 into actually minus 2. So, we can basically this will be plus 8, it is not minus 2, c is equal to minus 2 f1 square. Well, so, that can be divided by twice a means 2 into 1, divided by twice a means 2 into 1. So, that can be written as y2 by y1 is equal to half we are bringing here, and then this term I am writing first, root over 1 plus this is with root bracket 1 plus 2 into 4. So, minus minus plus. So, 8 f1 square, and then out of this plus minus sign, we will have to use this plus sign here. We cannot write plus minus. The reason is that if we write minus sign, then it is minus and then again minus. So, minus minus, I think this will be this ratio y2 by y1 cannot become negative. In no way it can become negative. So, this we cannot use the minus sign. So, this we are using the plus sign only. Minus sign is not practically possible because there is minus 1. If we use minus sign, then minus and minus, ultimately this ratio will become negative, which is practically not possible. So, this is the very popular expression. This is the very popular expression for relating this y2 and yn, which are the sequent depth of hydraulic jump. This is y1 and this is y2. And in free flow condition, that is, the jump will just start from this point where the depth is 1 and it will end at this point where the depth is y2. And we know that when we draw specific force diagram, and energy is not equal between this point and that point, because there are a lot of loss of energy in this portion. So, energy is not equal, but the specific force, we are starting from specific force equation and we are starting with the condition that specific force at upstream and downstream are equal. So, this y1 and this y2 we are talking about. These are for same specific force. This is specific force, this is depth y, and this depth is of course critical. This is critical. This is critical depth yc, and one of the depth is, that is, this depth is in subcritical region. This depth is greater than critical depth y2, and this initial depth is lower than critical depth. So, that we need to know. Y1 is called initial depth, y2 is called sequent depth, and of course, as a together y1 and y2 we call sequent depths of hydraulic jump, and conjugate depth also it is said that these are called conjugate depth. Okay. With this very introduction to the equation of equation of the hydraulic jump, here we should remember one point, that this equation we are writing very popular, but it is for rectangular channel. If it is not a rectangular channel, rather a trapezoidal channel, then we cannot have our equation in this form. Then we will have to go, we will have to derive, of course, till we can derive the relationship between y1 and y2 for trapezoidal section. But in that case, we will have to start from the very basic principle that specific force is equal, specific force at upstream here and downstream. That is what we are writing here, at the specific force at upstream and downstream are equal. Based on that, we will have to start, and then from there we need to compute the depth of upstream and downstream. Once we know the upstream depth, we can compute the downstream depth, and that we can do by trial and error procedure for trapezoidal channel. Of course, some graphical procedures were developed and some approximate solutions were also developed. In fact, we also tried to develop one approximate solution, empirical solution, generating lot of data in laboratory channel, and then of course by computation also by mathematical model we did develop lot of data for y1 and y2, and we then tried to see how this can be related empirically, and we could relate it based on the discharge value. Of course, this equation is valid for a definite range of channel, maybe in the level of irrigation canal this is valid, but we cannot say in general. That is why I am not putting that here. Anyway, so these relations can be used. Now, with this understanding of hydraulic jump, now we can go for the classification of hydraulic jump. You can go for classification of hydraulic jump. Well, hydraulic jump can be classified in different way on the basis of different rather on different basis. So, one classification of hydraulic jump that we carried out, this is based on the tailwater depth. And proper understanding of this particular classification is very important. Well, this way we classify the jump as free jump, then next is repelled jump, and then we talk about another jump which is called as submerged jump or drowned jump. Well, just let us see how this tailwater depth is significant and how it influences the hydraulic jump. Well, say we have a y1 here. Now, let us refer to the specific force diagram. This is the specific force diagram and this is y1. This is y2. Now, what it indicate? This is specific force in this side, that is specific force F we are talking about, and on this side we are putting the depth y. Well, and sequent depth means this y1 and y2. Well, now this means that if this depth is y1 we are fixing, and we know that this is supercritical flow, this is supercritical flow, and at tailwater means at a downstream side, this depth must be subcritical. This depth must be subcritical. Then only hydraulic jump will form. Otherwise, if on the downstream also suppose we have supercritical flow, then there will not be hydraulic jump. There will be a gradually varied flow profile in that case. Well, now somehow here the tailwater depth is say this much. Tailwater depth is this much. And we are writing this tailwater depth as y2 dash, y2 dash. Okay, we are not writing this as y2, but y2 dash, because this tailwater depth will be governed by some other condition, that is in the site, whatever we are barrier we are putting, how we are increasing the depth of the tailwater, maybe some barrier we are putting here and increasing these things, or maybe the channel is of the type that here by some sluice gate on the upstream, suppose we are creating this y1, but the normal channel flow will be like that, say downstream uniform flow will be this much. So, by various region, due to various region we can have the tailwater depth. This is coming from the physical process, and that is what is y2 dash. Now, we know that hydraulic jump will occur from this y1 depth to its sequent depth y2, Now, if this y2 dash, that is the tailwater depth, is equal to, if this tailwater depth y2 dash is equal to the sequent depth, we do not know what this sequent depth is. If this tailwater depth is equal to the sequent depth y2, but this y2 is sequent depth corresponding to y1. So, for different y1, suppose if our y1 is here, our sequent corresponding depth, or its corresponding sequent depth, will be this one. So, for each of our y1 which is in supercritical condition, it has a corresponding sequent depth, say this one. And one interesting point is that when our, this is critical flow, when our initial depth increases, say initial depth is increasing like this, this is y1, then it can come here. When our initial depth is increasing, then its corresponding sequent depth is decreasing. So, for one particular initial depth, there will be a sequent depth. Now, if tailwater depth is equal to the sequent depth, then say this y2 dash or now we can write like this: if this y2 dash tailwater depth is equal to y2, then from here that it is its corresponding sequence depth is this one, so it will jump like this, and this part we are getting lot of turbulence, and this sort of jump we name as free hydraulic jump. Free hydraulic jump. We are not forcing the hydraulic jump to occur in a particular place. We are not doing anything. Our tailwater depth is just equal to the required sequence depth for this initial depth, and that's why the jump is occurring freely, and we call this jump as free jump. Now question is that if this depth is tailwater depth is higher than this one, now for this y1 sequence depth is y2, that is fixed, but tailwater depth may be more than that, tailwater depth may be less than that, then how the hydraulic jump will occur, that we need to understand, and understanding that only we can classify the hydraulic jump into other type, that is what is a repel jump, what is submerged jump. So that we will be discussing in the next class, and then we will continue with our this most interesting topic hydraulic jump in the next class also. Thank you very much.